Hello friends, in the last lecture we talked about the basic operation of BJT as an amplifier and as a switch. Then we talked about phototransistor and finally the transistor categories and packaging. In today's lecture we shall discuss the transistor bias circuits. As you learned previously, a transistor must be properly biased in order to operate as an amplifier. DC biasing is used to establish fixed DC values for the transistor currents and voltages called the DC operating point or Q point. This discussion would lay the foundation for the study of amplifiers and other circuits that require proper biasing. After we complete this discussion, you would be able to determine the DC operating point of a linear amplifier, analyze a voltage divider bias circuit and analyze an emitter and base bias circuits. DC bias. Bias establishes the DC operating point or Q point for proper linear operation of an amplifier. If an amplifier is not biased with correct DC voltages on the input and output, it can go into saturation or cutoff when an input signal is applied. Figure here shows the effects of proper and improper DC biasing of an inverting amplifier. In this figure, the output signal is an amplified replica of the input signal, except that it is inverted, which means that it is 180 degrees out of phase with the input. The output signal swings equally above and below the DC bias level of the output VDC out. Improper biasing can cause distortion in the output signal as illustrated in parts B and C of figure. Part B illustrates limiting of the positive portion of the output voltage as a result of a Q point being too close to cutoff. Part C shows limiting of the negative portion of the output voltage as a result of a DC operating point being too close to saturation. Graphical analysis. The transistor in figure here is biased with VCC and VBB to obtain certain values of IB, IC, IE and VCE. The collector characteristic curves for this particular transistor are shown in part B of figure. We will use these curves to graphically illustrate the effect of DC bias. Here we shall assign 3 values to IB and observe what happens to IC and VCE. First, VBB is adjusted to produce an IB of 200 microamperes as shown in figure. Since IC is equal to beta DC into IB, the collector current is 20 milliamperes as indicated in the figure, and VCE is equal to VCC minus IC into RC. Substituting the values of VCC and IC RC, we get VCE equal to 5.6 volts. The Q point is shown on the graph of figure as Q1. Next, as shown in figure, VBB is increased to produce an IB of 300 microamperes and an IC of 30 milliamperes. Here VCE becomes 3.6 volts. The Q point for this condition is indicated by Q2 on the graph. Finally, as in figure here, VBB is increased to give an IB of 400 microamperes and an IC of 40 milliamperes, then VCE becomes 1.2 volts. The corresponding Q point is shown on the graph as Q3. DC load line. The DC operation of a transistor circuit can be described graphically using a DC load line. This is a straight line drawn on the characteristic curves from the saturation value, where IC is equal to IC saturation on the y axis, to the cutoff value, where VCE is equal to VCC on the x axis, as shown in figure. The load line is determined by the external circuit VCC and RC, not the transistor itself, which is described by the characteristic curves. The equation for IC becomes as shown here. This is the equation of a straight line with the slope of 1 upon RC and x intercept of VCE is equal to VCC and a y intercept of VCC over RC, which is IC saturation, the point at which the load line intersects a characteristic curve represents the Q point for that particular value of IB. Linear operation. The region along the load line, including all points between saturation and cutoff, is generally known as the linear region of the transistor's operation. As long as the transistor is operated in this region, the output voltage is ideally a linear reproduction of this input. Figure here shows an example of the linear operation of a transistor. AC quantities are indicated by lowercase italic subscripts. Assume a sinusoidal voltage V in is superimposed on VBB, causing the base current to vary sinusoidally above 100 microampere and below its Q point value of 300 milliampere. This in turn causes the collector current to vary 10 milliampere above and below the Q point value of 30 milliampere. As a result of the variation in collector current, the collector to emitter voltage varies 2.2 volt above and below its Q point value of 3.4 volt. Point A on the load line corresponds to the positive peak of the sinusoidal input voltage. Point B corresponds to the negative peak and point Q corresponds to the 0 value of the sine wave. VCEQ and ICQ and IBQ are DC Q point values with no input sinusoidal voltage applied. Voltage divider bias. Now we will discuss a method of biasing a transistor for linear operation using a single source resistive voltage divider. This is the most widely used biasing method. After completing this section, you should be able to define the term stiff voltage divider, calculate currents and voltages in a voltage divider biased circuit, explain the loading effects in voltage divider bias, describe how DC input resistance at the transistor base affects the bias, and finally apply Thevenin's theorem to the analysis of a voltage divider bias. Up to this point, a separate DC source VBB was used to bias the base emitter junction because it could be varied independently of VCC and it helped to illustrate transistor operation. A more practical bias method is to use VCC as a single bias source as shown in figure. To simplify the schematic, the battery symbol is omitted and replaced by a line termination circle with the voltage indicator VCC as shown. The DC bias voltage at the base of the transistor can be developed by a resistive voltage divider that consists of R1 and R2. VCC is the DC collector supply voltage. Two current paths are between point A and ground, one through R2 and the other through the base emitter junction of the transistor and RE. Generally, voltage divider bias circuits are designed so that the base current is much smaller than the current I2 through R2. In this case, the voltage divider circuit is very straightforward to analyze because the loading effect of the base current can be ignored. A voltage divider in which the base current is small compared to the current in R2 is said to be a stiff voltage divider because the base voltage is relatively independent of different transistors and temperature effects. To analyze a voltage divider circuit in which IB is small compared to I2, first calculate the voltage on the base using the unloaded voltage divider rule as given here. Once you know the base voltage, you can find the voltage and currents in the circuit as shown here. VE is equal to VB minus VBE and IC is approximately equal to IE and is equal to VE upon RE. Then VC is equal to VCC minus IC into RC. Once you know VC and VE, you can determine VCE by this equation. VCE is equal to VC minus VE. The basic analysis developed in this example is all that is needed for most voltage divider circuits, but there may be cases where you need to analyze the circuit with more accuracy. Ideally, a voltage divider circuit is stiff, which means that the transistor does not appear as a significant load. All circuit design involves trade-offs, and one trade-off is that stiff voltage dividers require small resistors, which are not always desirable because of the potential loading effects on other circuits and added power requirements. If the circuit designer wanted to raise the input resistance, the divider string may not be stiff and more detailed analysis is required to calculate circuit parameters. To determine if the divider is stiff, you need to examine the DC input resistance looking in at the base as shown in the figure here. Loading effects of voltage divider bias. The DC input resistance of the transistor is proportional to beta DC. So, it will change for different transistors. When a transistor is operating in its linear region, the emitter current IE is beta DC into IB. When the emitter resistor is viewed from the base circuit, the resistor appears to be larger than its actual value because of the DC current gain in the transistor. The effective load on the voltage divider is given by this formula. You can quickly estimate the loading effect by comparing R in base to the resistor R2 in the voltage divider. As long as R in base is at least 10 times larger than R2, the loading effect will be 10% or less and the voltage divider is stiff. If Rn base is less than 10 times R2, it should be combined in parallel with R2. Thevenin's theorem applied to voltage divider bias. To analyze a voltage divider biased transistor circuit for base current loading effects, we will apply Thevenin's theorem to evaluate the circuit. First, let us get an equivalent base emitter circuit for the circuit in figure here using Thevenin's theorem. Looking out from the base terminal, the bias circuit can be redrawn as shown in figure B. Apply Thevenin's theorem to the circuit left of point A with VCC replaced by a short to ground and the transistor disconnected from the circuit. The voltage at point A with respect to ground is given by this equation and the resistance is given by this equation. The Thevenin equivalent of the bias circuit connected to the transistor base is shown in part C of the figure. Applying Kirchhoff's voltage law around the equivalent base emitter loop gives Vth minus Vrth minus Vbe minus Vre is equal to 0. Substituting using Ohm's law and solving for Vth, Vth is equal to Ib into Rth plus Vb plus IeRe. Substituting IE over beta DC for Ib, we get this equation as shown. Then solving for IE, we get the equation as shown here. If Rth over beta DC is small compared to Re, the result is the same as for an unloaded voltage divider. Voltage divider bias is widely used because reasonably good bias stability is achieved with a single supply voltage. Emitter bias. Emitter bias provides excellent bias stability in spite of changes in beta or temperature. It uses both a positive and a negative supply voltage. To obtain a reasonable estimate of the key DC values in an emitter biased circuit, analysis is quite easy. In an NPN circuit such as shown in figure here, the small base current causes the base voltage to be slightly below ground. The emitter voltage is one diode drop less than this. The combination of this small drop across Rb and Vbe forces the emitter to be at approximately minus 1 volts. Using this approximation, you can obtain the emitter current as minus Vee minus 1 volt over Re, where Vee is entered as negative value in this equation. You can apply the approximation that Ic is approximately equal to Ie to calculate the collector voltage, and that is Vcc minus Ic into Rc. The approximation that Ve approximately equal to minus 1 volt is useful for troubleshooting because you won't need to perform any detailed calculations. In the case of voltage divider bias, there is more rigorous calculation for cases where you need a more exact result. The approximation that Ve is approximately equal to minus 1 volt and the neglect of beta DC may not be accurate enough for design work or detailed analysis. In this case, Kirchhoff's voltage law can be applied as follows to develop a more detailed formula for IE. Kirchhoff's voltage law applied around the base emitter circuit in part A of figure here, which has been redrawn in part B for analysis, gives the following equation: VEE plus VRB plus VBE plus VRE is equal to 0. Substituting using Ohm's law, VEE plus IBRB plus VBE plus IERE is equal to 0. Substituting for IB and transposing VEE, we get this result: IE over beta DC into RB plus IERE plus VBE is equal to minus VEE. Factoring out IE and solving for IE, we get this equation. The emitter voltage with respect to ground is equal to VEE plus IERE. The base voltage with respect to ground is equal to VE plus VBE. The collector voltage with respect to ground is equal to VCC minus ICRC. So, friends, here we come to the end of our discussion in this lecture, and therefore, we sum up. The purpose of biasing a circuit is to establish a proper stable DC operating point called the Q point. The Q point of a circuit is defined by specific values for IC and VCE. These values are called the coordinates of the Q point. A DC load line passes through the Q point on a transistor's collector curves intersecting the vertical axis at approximately IC saturation and the horizontal axis at VCE off. Loading effects are neglected for a stiff voltage divider. Voltage divider bias provides good Q point stability with a single polarity supply voltage. It is the most common bias circuit. Emitter bias generally provides good point stability, but requires both positive and negative supply voltages. So, that is it for today. Thank you very much.